So you know where we're up to with this is you've done an excellent job with that. I was very pleased to see the imagination things you guys showed about putting that together, creativity. And what a lot of people think is that science is just dead serious, where it's actually about playing and using creativity to learn things. That was great. So what I need you guys to do is I need copies of those files with the videos so I can then put them.
Energy effects.
Yeah, you know, no.
So we should do that and then we have it. Make sure that
Yeah, all right. But anyway, we've got to. Thank you, Tom. Thank you, Tom. The point of it, of course, was to show the stuff that old video from the 1960s was showing, that if you came moving with it, it would look like it's falling straight down. If you're moving from the side, it would look like it's moving in a parabolic curve. But don't forget, for you guys, no, it won't, because when you do it, right, what we automatically do is we go with our eyes, pick the easiest frame. So because we're looking at the mast moving along, we compare the motion with the mast. And so we see the ball fall straight down. But when from the video, if you actually put dots down at equal time frames from where Riley was sitting there stationary as the thing went by, you'll actually see it will go in a parabola. So even though we look at it and say, oh, it fell straight down, it actually doesn't. It moves in a curve. And this is the stuff that Galileo was saying. Now, we're in a bit of a rush, though, to get through some of the other stuff. Well, I know for some of you, maths is boring. Okay, a lot of people, maths is not their natural language, but it is a language. Now, the importance of this maths, though, is it's all very well to be able to observe something and make some description of what's going on. But in the end, what you want is a language you can use to make predictions with it and work things out. So you don't want to be lining rockets up on a launch pad, loading up with fuel and guessing where you're going to shoot it, and the first 25 don't go where you want it, and you do it by trial and error, because it will cost you $25 billion to do that. It's a bit expensive. So there are kind of. So what we want to do is we need to develop a mathematical language which allows us to take what we observe, generalise it, and then use it to make predictions or as a tool to make things happen.
Sir,
so, yes?
a boat does not travel that fast to see that path.
No, this is just someone's picture of it. This is out of Surfing Science, and it is a summary of the stuff Galileo was talking about. And people have been concerned about the syllabus. The syllabus, if you look at it, which I'll bring up, doesn't say an awful lot about Galileo. Describe Galileo's analysis of projectile motion is what it says, and that's all it says. But behind that dot point, there is an awful lot of assumptions made. And they've asked questions in the past which requires you to know all the stuff we've gone over. So if I only said to you, Galileo said horizontal and vertical were independent, that wouldn't be enough very often to get through the HSC. That's why we're doing the detail.
So in space, is this page what usually takes up the longest time?
No, this takes equal longest time. This part here takes quite a lot of time. And even though it's not, it doesn't say a lot about those formula and whatnot, this part about these 2 dot points here take an awful lot of time. And the other part of the syllabus which takes a lot of time is that bit. Just that dot point there takes a lot.
Is it true that Galileo said measure what is measurable and make measurable what is not so? So I was playing a game last night, and you make your civilization, you research all the technology, you research physics, and come up and said that Galileo, that was his famous words.
My short answer to that is I don't know. He could have. So often what happens too is that quotes by other people are attributed to famous people. So sometimes it goes wrong. Okay. Now, first things first. In doing any question to do with objects falling or being thrown or any motion inside the gravity field of Earth or any other planet, there's a skill that you need to be able to do any question to do with that. All right? On the board over here are a series of formulas which should look fairly familiar to you. We use those sort of formulas in doing motion and moving about. Okay, and if they're not, they might They might, yes you did, but not in the form you recognise here. But you have actually done them, and we're going to use them in more detail as we go through this dot point. So it's to do with working out distances travelled and things like that when you accelerate. And a lot of this stuff you did intuitively. Because I said to you things like, that's really annoying. I said to you things like, if a car started at this speed and then accelerated for this long at this speed, how far would it end up travelling? You were able to work that out. They're the formulas that describe it. But before we get to that, if you take an initial a velocity, right? So say it's the ground, and someone fires or kicks. Let's make it a football. They kick it. They kick it at an angle from the ground, theta, and it has and it has an initial speed, right? U is the symbol for initial speed. Now, because it's straight U, that just means that vector there. Now, don't forget, that vector does not describe the path that ball is taking. Right? What that vector does is it says at that point there where it started, it tells you how fast it was going in what direction. It doesn't tell you the path.
I can't really see where you're drawing.
Sorry. So that vector there's the ground,
Yep.
horizontally across. And I'm saying that someone kicked a football like they did in the weekend in Country City. And they kicked at a certain angle at a certain speed. That straight line is not the path the ball took. Okay? What it says is at that point there, that ball had a velocity u in that direction. That's what it says. Someone's mucked up mine. So that's the instantaneous speed at that point. It's not the path the ball is taking. If you kick it like that, the path of it, of course, will be some sort of curve like that, won't it?
Yeah.
Yep.
Could go up.
Not when you kick it at that angle.
Depending on how you kick it.
The gradient at that point.
That's right. So there's the ground in blue. Here's the starting vector again, and an angle theta. Now I've done it generally for a reason. Now don't forget, any vector can be described by two other vectors, can't it? Added together. Or 3 or 4 or 5 or 20, whatever. But I'm going to use 2 in this case because it's convenient. Because what Galileo said to us was that for that speed or velocity going that way, right? Sorry, I'll try and get out of your way. There was a horizontal bit to it, which was that big, and a vertical bit, which is that big, which we would call uy and ux. So ux, of course, meaning speed horizontally, and uy meaning speed vertically.
Why is it U?
U is just the symbol we use for starting speed in this syllabus. If you use it, it's the one we use in New South Wales for some reason. In lots of other places, they might use the symbol V0, or they might use VI.
So in the HSC, it's going to be UX.
It's going to be UX and so on. Okay. Now, the question is, Galileo said that speed sideways is the speed that ball's going to go for its whole journey, isn't it? But that speed vertically is going to change because of gravity, the force of gravity acting on it. And we need to be able to work out for a whole series of, or for any question, what's initial sideways or horizontal speed is, and what its initial vertical speed is. Now there's a very, very simple bit of trigonometry you can use to work this out. So I'll duck over and get in the way of people this way now. So, if I wanted to find the sine of theta, what will it be on this diagram?
Sine of theta being UY over U.
UY
UY over U.
over U. That means to find Vy, I rearrange this U comes to the in front of the sign. So uy will be, whoops, u sine theta. Yes, I do. Now, what about the cos? That'd be the ux
Yeah, Jason. So UX over U.
over u. So cos theta will be, cos of that theta will be ux over u. So I can rearrange that. So ux
So it's all about.
is going to be u cos theta. Okay? So when I want to find out what the size of uy is, I'll use u sine theta. When I want to find out the size of ux, I use u cos theta. So let's have a look at in this table, this is exactly what you're trying to do. So they tell you in the first one that you have a launch speed of 50 meters per second at 60 degrees to the horizontal. So no, this is what we're going to be working through in the next couple of lessons, this stuff. So let me do the first one with you. If I drew it, there's the ground in red, just because I can. And there's going to be something launching at about 60 degrees, which is something like that. 60 degrees in there. And it will have a speed of 50 meters per second starting at that angle, right?
Yeah.
Okay. So they want you here to find out A and B, the horizontal and vertical components. So if I drew those in, that's one component. And they call these components. There's the other component. I'm going slowly to make it easy. So A is the horizontal, which is that. B is the vertical, which is that. So to find out A, which is the horizontal component, will equal u cos theta, which will be, 50 cos 60. And if we had Riley here, I'm sure he'd tell me that cos 60, I'm thinking it's probably 0.8660, isn't it? So I'll put it in my calculator. 0.5, okay. So that makes it easy. 0.5 times 50 is 25. So the initial horizontal speed here is 25 meters per second. Now to find out the B, which is the initial vertical speed, uy, which is u sine theta, which is 50 sine 60, which equals,
50 times root 3 on 2.
yep, so 50 times sine 60
Looks like there's a dust storm.
is 43.3. Okay, so that's how you do the first one relatively easily. How do you go back the other way? Because you might notice in this question, you are not given the launch speed in question 3, and you're not given the vertical.
75 to 8. No.
Well, let's
10, negative 10, no, 10, negative 10, 20 over 75.
let's have a quick look. First thing you want to do in any question is what?
Write out what you have.
Draw the picture and write out what you'd have. So you're going to have horizontal. Question 3, you have something called E, which is some vector like that. You know that the horizontal is 75, so that bit there is 75.
Degrees.
Oh, angle. Oops. That's 20, isn't it? That bit there is 75 degrees, thank you.
Are we figuring out?
And
what are we figuring
what's the horizontal component? 20, so that's 20 there.
That's not a problem.
That's a triangle.
Why are we trying to find a triangle?
Because it always is a triangle.
But it's trying it's a vector.
So I'm trying to find E. I'm trying to find the length of E.
Are you trying to find the initial angle when it's first kicked?
No. I'm told the angle.
Vertical force.
And I'm trying to find the initial speed. I'm trying to find out the size of that bit of the triangle. And I'm trying to find out that bit there. So to find out E, we know that E cos theta is going to equal what? It's cos, so it's going to equal 20, that's right. And we know theta is 75, so that means that E will equal 20 divided by cos 75. Okay, simple rearrangement. And you can put that in your calculator and get the answer out. Once you know what E is, finding F, how much? 77 point?
77.27, 77.27
And once you know that one, then finding F is easy because it's just,
Well, 20 squared plus 77.27 squared equals 80 squared.
let's get my labelling right too. Yeah, try and find F. So F in this case, F will just simply be the 77.27 sine of 75, won't it?
Why not just do Pythagoras?
You could just do Pythagoras if you wanted.
Weird, it's got F being 74.64.
Yeah, so that means that its vertical speed is greater than its horizontal speed. But you have an angle of 75, you'd expect that, wouldn't you? It's short that way and long that way.
What's the horizontal? I don't understand this. I thought you said this was proper. It's like integers.
No, I didn't say it was a parabola. What I said is that it's two vectors adding together to make the original one. So Tom, what I'm saying is that,
That's not a path of motion. That's just the horizontal line.
yeah. So look, what I'm saying, Tom, is that, yeah. So when it starts off at that point, it will have a velocity which I can represent as a vector. And the vector I can represent as a straight line, and that's only at speed at that point there, right at this beginning. So it will have an initial speed.
What if there was a question that said 2 seconds into its flight, what's its velocity?
You'll be doing that next lesson.
Oh, cool.
Okay, so once I got that, what I'm saying is Galileo told me and others is that I can break this into two parts, the horizontal part,
Did he tell you that question?
yeah he did, and the vertical part. And then you can calculate the size of that and that.
Yeah, okay.
Okay, right, so bell's about to go, is it?
Are we back in here, sir?
So, oh, we're actually back over
Is
there.
there a class next?
Uh,
Is there a class in here?
I haven't actually ever checked to know, so I don't know.
Then wouldn't it be easier if like you say,
I go over hill.
well, usually when we have to class, there's a bus temporary, so you have to have